Hello everyone, welcome to this lecture. So, just to recall, in the last lecture we had introduced the key exchange problem and we have seen various security notions, and we have also seen the idea involved behind the Diffie-Hellman key exchange protocol. Although we have not yet seen the exact mathematical details, but we have seen how, given some special functions E and F, how we can design Diffie-Hellman key exchange protocol. Now, what we are going to do here is we are going to continue our discussion on the key exchange protocols, and we will see generic constructions of key exchange protocols. Namely, we will see constructions based on one way trapdoor functions, which are a very nice mathematical primitive, a fundamental cryptographic primitive, which are more powerful than the notion of one way functions. So, what exactly are one way trapdoor functions? So, before going into the definition of one way trapdoor function, let us first recall the definition of one way function or OWF. So, a one way function f is a publicly known function, a deterministic function from the domain fancy x to the codomain fancy y, and the requirements for this from this one way function are that it should be easy to compute for any value little x from the domain x, whereas it should be difficult to invert in polynomial time any random input from the range set of f. That means, if someone gives me a y which belongs to the range of f and y is randomly chosen, then in poly time it should be difficult to come up with some at least one image for this input y. Now, what exactly is one way trapdoor function, right? So, it sounds like a special type of function, and indeed it is a special type of one way function which is also have an associated trapdoor information. And what exactly this trapdoor information is going to help you with? Well, it helps you to invert any input from the range set of the function f, provided you have the knowledge of the trapdoor information. That means, any entity who knows the description of this trapdoor information, then it can easily invert the function f on any random y from the range set of f. But in the absence of the trapdoor information, the function looks like a one way function to that entity. It will not be possible for that entity who does not possess this trapdoor information to invert this function f on any random y from the range set of the function f. So, now let us try to formally state this requirement, what exactly we mean by this special trapdoor information, and it easy to invert in the presence of the trapdoor information and difficult to invert in the absence of the trapdoor information. So, when we say that we have a trapdoor function scheme tau, then it is over a pair of finite sets where x will be the domain of the function and y will be the codomain of the function. And when we say a trapdoor function scheme, basically we mean a triplet of algorithms, all polytime algorithms, polynomial in some security parameter. The first algorithm is the key generation algorithm, or basically parameter generation algorithm, and the function f is the function in this underlying, which in this underlying context will be a one way function, and corresponding to the function f we have an inversion function. So, syntactically the parameter generation algorithm or the key generation algorithm is a randomized algorithm which does not take any explicit input, but internally it has some internal random, it generates internal random coins, and based on the value of the random coin it output a pair of keys or pair of values which I denote by pk and sk. So, pk is going to be the public key which will be available in the public domain, and sk will be the secret key which will be known or which will be available only to some designated entity with some designated entities. Now, what is the function f? Well, it is a function from the set fancy x to the set fancy y. So, it is a function parameterized by a public key pk. So, anyone can evaluate this function provided it knows the description of the function and the description of the public key pk, and the function takes an two explicit inputs, namely the input x on which the function needs to be evaluated and the public key, and it gives you an output which I denote by little y, and this little y will be an element from the codomain set fancy y, and it is a deterministic algorithm. That means, every time you evaluate this function little f with the same input little x and with the same public key pk, you will obtain the same output y. There is no randomness which is there as part of the algorithm. Now, the inverse algorithm, it is also a two input function. It takes an input y from the set fancy y which you want to invert and the secret key sk. That means, this function can be invoked only by an entity who possesses the secret key, which actually in our context is the trapdoor information. If you do not have the secret key or the trapdoor information, then you will not be able to invoke this function. So, assuming that an entity who knows the function input y on which this function inverse has to be invoked also knows the trapdoor information, it runs the function with this inputs sk and y, and it is going to either obtain an input it is going to obtain either an output little x or a special status symbol bot, which denotes an invalid input, right. So, if the output of this inverse function is not bot, then it is going to be an element from the domain of the function little f, namely it is going to be an element of the fancies x, whereas if the output is bot, then it indicates an invalid input, and we will soon see what exactly we mean by an invalid input with respect to the underlying context. And this inverse function is always going to be a deterministic algorithm. That means, if you invoke this inverse function with the same little y and the same secret key sk, then you are going to obtain the same output again and again. Now, what are the properties we require from this one way trapdoor function? The first property is the correctness property, which says that for every pair of parameters or keys pk comma sk generated by your key generation algorithm, and for every input little x from your domain of the function f, if you invoke the function on the input x with respect to the key pk and the resultant output is say denoted as y, and then if you try to invoke the function inverse on the input y and with the secret key sk or the trapdoor information sk, then the output should be the same input x, and this should hold for every pk comma sk generated by your key generation or parameter generation algorithm. Now, notice that as soon as we state this correctness requirement, it automatically means that your function little f, which is there as part of your trapdoor function scheme, has to be a 1-to-1 function. That means, if you have two distinct inputs x1 and another input x2, where x1 is not equal to x2, right, and if you try to evaluate the function f of pk on the input x1 and on the input x2, you can't get the same output y, because if both x1 and x2 gets mapped to the same output y under the function f of pk, then what happens when you try to invert the input y with the secret key sk? You can get back x1 with some probability, you can get back x2 with some probability, but that strictly goes against the correctness requirement. The correctness requirement says that you should obtain back the exact input with which you evaluated the function fpk and then try to run the inverse algorithm unambiguously, and that is guaranteed only if your function f of pk is a 1-to-1 function. However, notice that even though the function f of pk is a 1-to-1 function, that does not mean that the function has to be a onto mapping. There might be several possible inputs from your set go domain set fancy y, which may not have a pre-image under the function f, and that is why we have a special provision for the output of the inverse function to be a bot symbol. Because if we are trying to invoke the function inverse on some element little y which does not have a pre-image, that means this little y is not an element of the range set of your function f, then we should get the output bot, indicating that we are trying to invert something which does not have a corresponding pre-image, right. So, that is the definition of one way trapdoor function. So, we have seen the correctness requirement. Now, we have to model the one-wayness property, and remember the one-wayness property requires that any entity which possesses the secret key or the trapdoor information should be able to invert the function or compute the output of the function inverse on any y from the range set of the function f, but in the absence of the trapdoor information, it should be computationally difficult to compute the output of the inverse function on any y belonging to the range set of the function f, right. And this should hold even if that entity or that adversarial algorithm knows the description of the public key or public key pk. So, let us try to model this requirement by an experiment which we call as an invert experiment. This experiment is almost the same as the way experiment which we used to model the one-wayness property for one-way function, which does not have a trapdoor information associated with it, but it will now have some different security requirement here, or the output of the experiment is defined in a different way and the rules of the experiment are also slightly different here. So, what is known to publicly is the description of a trapdoor scheme, namely the triplet of algorithm gen f inverse and the domain and the codomain of the function little f. Now, the challenge is generated for the adversary is as follows. The challenger of the experiment runs the parameter generation algorithm to obtain the pair of public key and the secret key, and it picks a random x from the domain of the function f, and the challenge which is thrown to the adversary are as follows. The public key is given to the adversary and the value of the function f on the random input x, namely y, is also given as a challenge to the adversary. And the goal of the adversary is basically to compute the pre-image of this little y without knowing the corresponding secret key or the trapdoor information sk. So, basically adversary after polynomial amount of time is going to output some x dash from the domain of the function f, and we say that the experiment output is 1, meaning that the adversary has won the experiment if and only if adversary A is able to correctly come up with the input x which has given the output y. And my security definition is, we say that the function f, which is a part of your trapdoor function scheme, is one way if for any polytime adversary who participates in this experiment there is some negligible function in the security parameter such that the probability of that adversary winning this experiment is upper bounded by some negligible function, where the probability is taken over the random choice of the experiment, namely the randomness involved in generating the parameters pk comma sk and the randomness used for selecting the value of x here, right. So, basically the essence of this experiment is the challenge for the adversary is to come up with the right x even without knowing sk, and the security definition demands that if the adversary does not know the trapdoor information or the secret key sk, then except with some very small probability it should be computationally difficult for a polytime adversary to come up with the correct x. In the definition we do not bound the success probability of the adversary winning the experiment to be 0, because there is always a guessing strategy by the adversary who can just guess some random x dash from the set fancy x, and with some non-zero probability it may so happen that the guessed x dash indeed turns out to be the correct x. So, the best that we can hope for is that any polytime adversary should not be able to do anything better than guessing the random x on which the function f is evaluated to compute the challenge y. Now, once we have the definition of one-way trapdoor function, let us define a related notion, namely one-way trapdoor permutation OWTP, right. So, one-way trapdoor permutation is a special type of one-way trapdoor function where the domain and the codomain of your function little f are the same, namely the set fancy x and the set fancy y are same. And this automatically implies that your function f of sub pk is a 1 to 1 onto mapping, that means it is a bijection. This is because we know that if the function is a one-way trapdoor function, then the correctness property implies that your function has to be your function little f has to be a 1 to 1 function, it need not be onto function. But as soon as I ensure that my domain and the codomain are same, and if both codomain and domain are finite sets, which is indeed going to be the case for the constructions which we will see later, then if my x and y are same and they are finite, and if my function is a 1 to 1 mapping, then it automatically implies that the function is also an onto mapping, right. That means for every x I am going to have a unique image, and I cannot have two different x mapping to the same y, and for every y from the set y I am going to have a distinct x such that f of x would have given me that y. That automatically means that if I am considering one-way trapdoor permutation, then the output of my inverse function can never be a bot, because if indeed I am going to invoke my inverse algorithm on some input y belonging to the set fancy y, then since my function is a invertible function or it has its 1 to 1 onto mapping, I am always going to obtain an element x belonging to the domain of the function f, namely the fancy set x. So, bot cannot be a possible outcome here. So, that is the only difference for the case of one way trapdoor permutation. So, now assume for the moment that you have given a candidate one way trapdoor function. We have not yet seen how whether indeed we have not yet seen a candidate one way trapdoor function. Later on, when we will introduce number theoretic assumptions and number theoretic hard problems, we will see how we can we will see examples of one way trapdoor function, but for the moment assume that you are given a one way trapdoor function. We will see how using that one way trapdoor function we can design an anonymous key exchange protocol achieving the notion of weak privacy. So, what is publicly known is a description of a one way trapdoor function scheme over some finite sets x comma y, and the goal here is to design a key exchange protocol, namely a pair of protocols, one for the sender and one for the receiver, achieving the notion of weak privacy, where the resultant key is going to be where using this one way trapdoor function scheme, and the resultant scheme is going to be an element from this set y. And from the description of the one way trapdoor function, what exactly one way trapdoor function does? It allows anyone to evaluate the function f, but until and unless the other party owns the trapdoor information, it will not be possible to invert the output of the function f. So, now based on this intuition, it is very simple to come up with a key exchange protocol. So, the protocols pi sub s and pi sub r for the sender and the receiver respectively will be as follows. What the receiver can do here is it can run the parameter generation algorithm of the one way trapdoor function scheme and obtain the pair of public key and a secret key, and it can give the description of the public key to the sender here, right. And once the sender learns the description of the public key, what it does it picks a random x from the domain of the function f, and it knows the description of the function little f, and it now knows the public key pk. What it can do is it can just evaluate the function little f using the key pk and the input x and obtain output y, which it communicates to the receiver. Now, what the receiver can do is, since the receiver possesses the secret key or the trapdoor information sk, it can compute the output of the function, it can compute the output of the inverse function on the input y under the key sk, and it can obtain the same x with which has been used by the sender to compute the output y, and both sender and receiver can now output a common value or a common key, namely x. Now, the correctness of this key exchange protocol automatically follows from the correctness property of your one way trapdoor function scheme, right, because since we are in the passive world, right, the copy of the pk which has been communicated by the receiver to the sender will be an authenticated copy. It will be the same pk which receiver has generated, and the corresponding sk is used by the receiver to compute the inverse of y under the secret key sk. So, the correctness of this whole key exchange protocol follows from the correctness property of your underlying trapdoor function scheme, and the weak privacy of this whole key exchange protocol follows from the one wayness property of the underlying function f, right. So, if we have a polynomial time eavesdropper who eavesdrops the communication and take the protocol transcript. So, what exactly is the protocol transcript for the adversary? From the viewpoint of the adversary, it is a random pk whose corresponding trapdoor information sk is not known to the adversary, and the adversary is now seeing the value y, which is the output of the function f of pk on some random x, where the random x is not known to the adversary. And the requirement of the weak privacy is that the resultant x, which is the output for the sender and the receiver here, should not be known in its entirety to the adversary. We are not aiming here for the indistinguishability based secrecy definition. We are actually aiming for all or nothing kind of security requirement here, because we are in the weak privacy setting here. So, if at all the polynomial time adversary, by learning the public key pk and the function output y, can come up with x in polytime with significant probability, then it means that we have an instance of the weak privacy or the invert experiment, where a polytime adversary can win that experiment with non-negligible probability, which goes against the assumption that the trapdoor function scheme is a one way trapdoor function scheme. So, only with negligible probability this polytime eavesdropper could come up with the correct x, otherwise the x will not be known to the adversary, and that ensures that this key exchange protocol is indeed it gives you the notion of weak privacy. So, that brings me to the end of this lecture. Just to summarize, in this lecture we have introduced the notion of one way trapdoor function, and we have also introduced the notion of one way trapdoor permutation. So, one way function is a special type of one way function which is easy to invert on any random or any value from the codomain or the range set of the function, provided you have a special trapdoor information. But in the absence of the trapdoor information, it is very difficult to invert any random input from the range set of the function, and we had seen that if you are given a candidate one way trapdoor function, then we can design a key exchange protocol achieving the notion of weak privacy. Thank you.